Hi guys, this video is going to explain to you numbers in chemistry, more specifically accuracy and precision. So let us jump right in. So the definitions that we need to know here are the definitions for accuracy and precision. So accuracy is going to be the measure of how closely individual measurements agree with the correct answer. That's the key phrase right there. So we're saying basically how far off are we? Not from the data points themselves, but from what we were supposed to get. For example, if we're trying to calculate the density as 1, that would be our correct answer. Or in other words, we could talk about the theoretical answer. So you can assume that that's a theoretical answer. Precision is a little bit different, and what we're looking for is reproducibility. We're looking at how closely individual measurements agree with one another. Now, we don't care if they're right or if they're wrong. It doesn't matter. All that matters is our data set really tight, which means they're not very far away from each other, or are they just kind of scattered all over the place, and that would give a lot of uncertainty as far as our piece of equipment goes from one measure to the next. So ideally, we want high accuracy and high precision. So you can take a look at this set of data here. What we've got is we've got 1, 2, 3 different bar graphs, which are shown. I'm sorry, I'm trying to do something on here. Fabulous. So we've got 1, 2, 3 different bar graphs shown. One is inaccurate and imprecise. So it's a little hard to read. What you need to take a look at is here. See that blue line? That's like the real value that you were supposed to get. And then the average of all of the data is this pink line, and it's given to you up here. So it could probably be done a little better. Prentice Hall. Anyways, so we've got 3 different students here. We've got student A, student B, and student C. Student A is an absolute hot mess. Look, inaccurate, imprecise. They're inaccurate because their data is just all over the place. Also, the average of their data here is a bit far away from what would be considered to be the true mass right there. They're also very imprecise because if you look at the data, they're all over the place. You've got this one that's really, really high, and then all of a sudden, whatever's measuring this jumps really, really low for no apparent reason. It must be a scale. Then a little higher, then back, it's just really all over the place. It's a disaster. Student B is a little bit better, and this data is at least workable. And the reason for that is, well, it's really inaccurate. You can see the average of the data is far below the true value, but this is inherent in the piece of equipment. It's highly reproducible. You can see by all those numbers all kind of matching up with each other. So really all we need to do is recalibrate the piece of equipment and then we're good to go. So this is doable. It's not the worst thing in the world. Talking to you, student A. All right. Student C is the teacher's pet kind of person. Super accurate, super precise. Why is it accurate? Because the average of the data lies directly upon the true value, which is fabulous. And their data is really close together. It's really reproducible. So student C is like that person that I can go tell to go do something in the hallway, and I don't have to make sure that they're actually following directions. Okay. So let's do some calculations here. You're going to have to bear with me because I'm doing these calculations along with you in some cases. So when we're talking about percent error, percent error is, let me switch to the pen. Percent error is a measure of accuracy. So it's a measure of how accurate you are. What I want you to do with this formula is kind of bunk. It's got some absolute value signs, and I actually don't want you using those. Don't use me. Don't use me. All right, so for percent error, what we're going to have is we're going to have our theoretical value minus the experimental value over the theoretical value times 100. And that is actually incorrect. This is probably the worst formula I've ever seen. I want you to switch those two. what it should say is experimental minus theoretical over theoretical, because we want something to happen. If our value is going to be lower than the true value, I want your answer for your percent error to be negative. Okay, so the only way for that to happen is if your experimental comes first, if that makes sense. So throw the experimental before the theoretical. So the true formula should say experimental value minus theoretical value over theoretical value. And to reinforce the fact that we don't want those, we don't want absolute value signs. If our value is higher than true, so I'll say higher than true, we want our percent error to be positive. So it needs to reflect like on what side of the true value you are. Some teachers are going to do this different ways. I don't want you using the absolute value signs. I kind of change it year to year because I get different opinions on it, but this year I think I'm going to go no absolute value. All right, so what I want to do is I want to take a look at, what I want to do is I want to take a look at this right here. We'll leave that there and we'll take a look at this example. It says a student measures the mass and the volume of a piece of copper to calculate the density. According to his results, the density of copper is blah. The teacher told the class that the real density is blah. What is his percent error? All right, so using our new formula, thanks flip chart, percent error equals, the way that I kind of shorten this is EXP, experimental, minus true, which is the real value, over true, times 100. Okay, so let's just plug that in. The experimental one is going to be the one that you got in the lab. So if we look through, it says, according to his results, the density of copper is blah. So we're going to look at this friend as the experimental. So our percent error equals 8.37 grams per centimeter cubed. Notice how I'm using my units, and also notice how I wrote my formula. Minus the true value. So the true value, it says the teacher gave, was 8.92 grams per centimeter cubed over the true value of 8.92 grams per centimeter cubed. Then we get to times the whole thing by 100. And one thing that students fail to show all the time is that times 100 part. So really make sure that you get that. What I am going to do is I'm going to pull out my phone and I'm going to calculate that right now. 8.37 minus 8.92 equals, divided by 8.92 equals times 100 equals. All right, so the value that I got was negative, and that makes sense. Why? Because my value was lower than the true value. So, all right, my answer was negative, and I'm using sig figs here. What I did was subtraction on the top, that's fine, but I can put it all in my calculator at once, so I'm only taking sig figs at the end. The overriding rule here, if you're using both, is going to be multiplication and division. So if I look at all of my numbers, I get 3 sig figs right here, I get 3 sig figs right here, I get 3 sig figs right here, so by default I get 3 sig figs in my answer, so it's negative 6.17 percent error. And that is my answer. Ta-da! We win! All right, so that's how you find percent error. It's pretty straightforward. Let's take a look at a set of data, because this is a little bit different. If you're given a set of data, what you need to do first is you need to calculate the average of all of these things. So you've got 4 trials right here, and we've got 2 thermometers. We've got thermometer 1, which is right here, and we've got thermometer 2, which is right here, and we need to calculate the average of all of those sets of data, because I don't want to be calculating a percent error for each and every single trial. That is a waste of time. We might as well just calculate the percent error once and just be done with it. So I already calculated the percent error of this one, or the average I mean. It's 100.05 degrees C. So now I just need to do this other one. I'm going to do that in my calculator right now. 98 plus 98.00 plus 98.02 plus 97.99 equals divided by 4, which is a counting number, people. All right, 98 point, I'm going to keep the same number of decimals, 98.01. All right, 98.01 degrees Celsius. All right, so we're measuring the boiling point of water. It says calculate the accuracy or precision of both of the thermometers. I'm going to leave the precision for later. Let's just calculate the accuracy first, because accuracy is a lot easier. So let's shrink that down and move it over here. Yeah, I know, right? That was magic. I know. All right, so for percent error, for thermometer 1, let's do that. So we're going to have percent error equals, notice also that this one is actually written correctly. Go flip chart. Go me for showing my work. So EXP minus true over true times 100. Pardon my handwriting. This is a stylus and horrible. Now you know what to get me for my birthday. All right, so we got percent error equals experimental is going to be what we got. So what we got was 100.05. Again, I'm only calculating this once. I see kids do this all the time on the test. Why would you calculate percent error for every single trial? Just average them together and do it for that. I'm going to include my units in 2 degrees C. Minus the true value, the boiling point of water, is 100 degrees C. It's infinitely significant. It's a standard. Divided by, oh, that's, well, here. Yay! All right. And then times 100, which, seriously, those are dumb. Our percent error is going to equal 100.05 minus 100, which is 0.05% error. Ta-da! We win, everybody. Yay! Okay, so there's that one. I will let you calculate the accuracy of thermometer 2. Can already tell you that number is way further away than 100. So as far as which thermometer is the most accurate, that's going to be thermometer 1, because it's closest to the true value. Okay. By the way, I backed that up with calculations, didn't I? Hint, hint. All right. So now let's go on to calculating uncertainty, which is a measure of precision, how close our data points are to each other. So what I'm going to do is I already kind of copied and pasted this data table into the next slide. So here we've got the same data as before, and I just kind of want to run you through the calculations. It looks like a lot. There's a lot more involved in calculating uncertainty than there is in just the simple formula of percent error. So all I did was here, we got to take each thermometer separately again. So I'm going to take thermometer 1 and I'm going to do that one. I copied over the average that we had from last time as 100.05 degrees Celsius. Pretend there's a unit there. Because we're going to be using this quite a bit, this average. So here, down this column for thermometer 1, I wrote in all of the data points that we have. So we have 4 trials, 1, 2, 3, 4. I wrote all of these here, 1, 2, 3, 4. And what I'm doing from each one is I'm subtracting the average from it. So if you look, this whole column is the same number all the time, no matter what. What I'm seeing is how far are my data points from the average? So really what we're calculating here is we are calculating a deviation. So that's why I put that up there, deviation. So the deviations that you calculate, they don't need to be positive or negative. You can absolute value them too, because like I said, really what we're doing, it's going to be plus or minus in the end anyways, so nobody really cares. I just kind of left them as negative or positive. Again, I didn't really care. So I did trial 1 minus the average was negative 0.04 degrees C. Trial 2 minus the average 0.06. Trial 3 minus the average 0.03. Trial 4 minus the average 0.04. So now I've got all these deviations, and you do that for however many trials you have. You may have 4, you may have 10, you may have 2, doesn't matter. Then what we're going to do, once we have all these deviations here, we're going to take the average of those, the average of the deviations. And you've probably seen this before. Some of my worksheets I use this. This symbol here is the symbol for average. So this is the average of the deviations that we're calculating. So I just went through, add all those together, divide by 4, and then we're good. So your answer is 0.04 degrees Celsius. That makes sense here. Our final answer we need to do a couple like fancy pantsy things here. So first of all, that average of the deviations needs to be 1 sig fig only. We never have a plus or minus 0.056. We never have a deviation of 1.5. It's not a thing. You are either plus or minus 1 or you're plus or minus 0.5. You can't have anything higher than 1 sig fig. So this always has to be rounded to 1 sig fig no matter what. The final format of your answer needs to be, so I will write this in for you. This part right here is the average with units. Then we've got our plus or minus, always include that. Then here we've got our deviation average to 1 sig fig. That is the proper format for an answer in terms of measurement of precision, which is uncertainty. Now, I just wanted to show you really quickly, if you've got, so let's just, oh, that's really not helpful, whatever. If you've got another number, so say we've got another answer, some genius came up with it, 100.05 degrees C plus or minus 0.06 degrees C. If we were comparing the uncertainty of both, this trial would be more uncertain than this one because the average of the deviations is larger. That means there's going to be a larger spread in my data and therefore more uncertainty. So when you're looking at uncertainty, always look at just this last number, and you should be able to figure out the larger the number, the more uncertain it is. What I'm going to do is I am going to kind of leave this here for now, but what I want to see is I want to see you, if I go back here, ready? Let's see if I can do this. Meow, meow, meow. No one cares. Great. I want to take this. Yeah, buddy. And I want you to calculate, hey, get out of there. I want you to calculate the uncertainty of thermometer 2 for me. So find the average, find the deviations from the average the deviations, plus or minus 1 sig fig. I think you guys can handle it. Thank you very much. Bye-bye.